Hello, this pencast is going over a part of the enzyme kinetics review worksheet that I handed out. The key is available, but I wanted students to be able to see the explicit steps involved in case it wasn't clear. I'm dealing only with the Michaelis-Menten equation part of this review, questions 1 through 3 in this first section. It's posted on Moodle. So when you're solving these equations, the challenge is just reordering your variables in a way to get what you want on one side. You can do this using the Michaelis-Menten equation, which will be given to you. In some cases, you can also use Lineweaver-Burke. I found this particularly helpful for solving question number 2. But it is possible to use just Michaelis-Menten. So question 1 reads, an enzyme is characterized by a Vmax value of 3.14 seconds to the minus 1 and a Km value of 1.25 millimolar. What substrate concentration is necessary for the enzyme to turn over products at 75% of its theoretical maximum velocity? Really the key to this is just making sure in a biological example or in a real life example that you understand what variables are what. So what is unknown in this question? And what is known? So let's start with what's known. You can see we have a Vmax is known. That's 3.14 seconds to the minus 1. We also know the Km value, 1.25 millimolar. Concentration becomes important when you're dealing with two different variables with different concentrations. In questions 1 and 2, this is not an issue. But you'll see in question 3, it will become an issue, and so you will have to do some unit conversion. The last thing that we know is the concentration of substrate. We're interested in determining the concentration of substrate is what we're solving for. The last variable that you may not appreciate that you have been given is the turnover rate, the initial velocity. They tell you it's 75% of the maximum velocity. But VO is not just 0.75, you have to multiply it by the actual Vmax. When you do this, you should get 2.355 seconds to the minus 1. Okay, so if you look at Michaelis-Menten, we have everything. We have all the variables except substrate. So here we go. Excuse me, that should be down there. The initial velocity equals Vmax times the concentration of substrate over Km plus substrate concentration. You multiply both sides by Km plus concentration of substrate. You get VO. You do your FOIL times the Michaelis constant plus VO times the concentration of substrate equals Vmax times the concentration of substrate. Okay? Next, you want to get the concentration of substrate all on one side. So subtract this term from both sides, and you'll get, keep drawing the 0 too high, V0 times Km equals Vmax times the concentration of substrate minus V naught times the concentration of substrate. You can do reverse FOIL to take out your concentration of substrate, and then you'll get this equals concentration of substrate of Vmax minus V initial velocity, and then you just divide both sides by this to get V naught times the Michaelis constant divided by Vmax minus initial velocity, and then you just plug and chug. So initial velocity 2.355 seconds to the minus 1 times your Michaelis constant, which was given to you, is 1.25 millimolar, divided by Vmax, which is 3.14 seconds to the minus 1, times your initial velocity, which again is this should be a subtraction right here, minus 2.355 seconds to the minus 1. And something I would just make sure of is that your units actually do cancel to give you something reasonable. In this case, hopefully you can see that the s to the minus 1 unit goes away and you're left with a concentration, which makes sense because that's what we are interested in finding out. And if you do this math correctly, you should get 3.75 millimolar. Take a second and see if you can understand what this number actually means. So pause and describe what this number means. Okay, so at a concentration of 3.75 millimolar, we are at 75% of the Vmax. Right, so you could literally, if you wanted to think about this, you could think of drawing a Michaelis-Menten plot out. It's important to try and make sure that your numbers make sense even after you've calculated them. It's just a good way to double check that your answer seems reasonable. The Vmax was 3.14 seconds to the minus 1. And we started, so if you were to go half away, this value was 1.25 millimolar, and you can see we were trying to figure out the concentration associated with somewhere 75% of its activity. So 3.75 millimolar makes sense because it's greater. You would have to go over here on your curve. It sounds somewhat reasonable. Okay? Question number 2 reads, under normal conditions, an enzyme with a Vmax of 8.23 seconds to the minus 1 is able to turn over products at a rate of 2.36 seconds to the minus 1 when its substrate concentration is 500 micromolar. If a competitive inhibitor decreases the apparent Km for this enzyme by 20%, what will the new rate be at this same substrate concentration? So, again, what are your knowns? We have a Vmax equals 8.23 seconds to the minus 1. And then it gives you a rate, an initial velocity of 2.36 seconds to the minus 1 at a given substrate concentration of 500 micromolar. Okay. This problem is 2 steps. So this is step 1. Because if you look at your equation here, right, you have Vmax, you have initial velocity, and you have the concentration of substrate. It's not it's not explicitly stated, but you do need to initially solve for the Michaelis constant. So that's step 1. Before we even start thinking about the second part of the question, just solve for Km. Alright, so some more algebra. I keep putting the... You have your Michaelis-Menten equation. You want to solve for Km. I think in this particular case I actually elected to go with the Lineweaver-Burke equation because Km is already sort of nicely by itself. If you were able to do it just with the Michaelis-Menten equation, that's fine, but I'm going to show how I did it using the Lineweaver-Burke. So times 1 over the concentration of substrate plus 1 over Vmax Okay, so it's pretty simple algebra. Subtract each side by 1 over Vmax and then multiply by the concentration of substrate and then multiply by Vmax. So you end up having 1 over the initial velocity minus 1 over Vmax, this quantity, times the concentration of substrate times the Vmax equals your Km. You simply enter in all of the correct numbers. Your initial velocity is here, Vmax is here, substrate here, and Vmax again. You should get a Km of roughly 1.24 molar. Okay, so now that we have this value, you can now predict what turnover rates would be in the presence of an inhibitor that changes different parameters of your enzyme's kinetics. It could be Vmax, it could be Km. In this case, it's given to you. However, there's an issue that I pointed out in class. Not everyone was there, so I wanted to make it explicit here. It tells you that it's a competitive inhibitor. If you think of competitive inhibition and what this looks like on a Michaelis-Menten plot, if this were the half Vmax, this would be your Km. You should hopefully remember this is an instance where the Vmax doesn't change, but it takes a greater amount of substrate to get there. That's competitive inhibition. So your Km actually increases. So maybe you were only here in the presence of an inhibitor, and remember it comes up to roughly the same place. But this is without inhibitor, this is with an inhibitor that is competitive. The issue here, if you reread the question, is that it says if a competitive inhibitor decreases the Km. So in the solution that's provided, they essentially, you treat this as in the key as it stands. It's a decrease in the Km of 20% is 0.8 times whatever your given Km that you just solved for was. In class, I encourage students to think about it, and instead of decreasing by 20%, it would make more sense, since it's competitive inhibition, that it increased it by 20%. So I'm actually going to show what my answer was when I did multiply your Km by 1.2, the same as increasing by 120%. The Km, again, that you just solved for is 1.24 molar. And I got 1.492 molar. So this is our new Km. This is what we just kind of calculated here. In the presence of an inhibitor, this is how much the Km goes up. We started at 1.24 molar, and now in the presence of a competitive inhibitor, we're at 1.492. And then it is literally plugging and chugging. We don't have to actually rearrange terms in this case. You just take the Michaelis-Menten equation. I'll actually write it out this time. Initial velocity equals Vmax, which is 8.23 seconds to the minus 1, times your concentration of substrate. And they indicate in the question we're at the same substrate concentration that was required to get to your original Km, which is given to you up here. So we're interested in determining the initial velocity at a concentration of substrate that is 500 micromolar, and we divide by our new Km, which is 1.492 molar plus 500 micromolar. The value I got for this was 2.0678 seconds to the minus 1. And again, I ask you to take a second and think about this. Does this make sense? This is in the presence of an inhibitor. You can see we're at roughly 2 seconds to the minus 1, whereas here we started with 2.36. So it makes sense in that in the presence of an inhibitor, the initial velocity that is competitive, the initial velocity is less than the initial velocity in the absence of an inhibitor. For those of you who elected to go the route of actually decreasing by 20%, if you did your calculations, your rate was actually higher. Your VO was higher in the presence of your inhibitor compared to the initial velocity. And based on what you know of competitive inhibition, that should have been a red flag. For the purposes of the exam, there won't be a typo, but just another opportunity to try and relate the math to what I've talked about in previous pencasts about types of inhibition and the parameters that are changing. Okay, question number 3 reads, what is the maximum turnover rate for an enzyme with a substrate affinity of 24 nanomolar, which has a turnover velocity of 14.72 seconds to the minus 1, when the substrate concentration is 25 micromolar? You might be thinking to yourself, well, that's just dirty. Why are you trying to trick us with changing the units? Well, this is actually fairly common of how you would see this type of example presented in scientific literature. You end up working for pharma, or maybe you end up doing some type of enzyme research in the future. When the substrate affinity is so small, so again, the substrate affinity, they say substrate affinity, but you know that this is actually commonly used to describe the Michaelis constant. So they tell you it's 24 nanomolar. Quick question, if this were 24, if the substrate affinity were 24 nanomolar versus 24 micromolar, this is a good learning opportunity. Which has the higher binding affinity? Take a second and think about that. I'll actually write the question out for you. Which would have a higher affinity for substrate binding to enzyme? One that had a Michaelis constant of 24 nanomolar or 24 micromolar? Pause. Basic, but, well, let's go there. Right? If we're thinking of molarity, which is moles per liter, you start with molar. As you get smaller, it becomes millimolar. As you get even smaller, we're at micromolar, and then nanomolar. Each of these is we're getting smaller by a factor of 1,000. So, which of these is smaller? Micro or nano? Nano. So you can see that this has a very small Km, and if you think about what Km means, it's the concentration required to get to half max. Something with a smaller Km, which would be indicated on the curve on the left, has a higher binding affinity. So the answer is 24 nanomolar would be a higher binding affinity, a much higher binding affinity, by a factor of 1,000-fold. A lot of times, if you're studying substrates or inhibitors where it binds very tightly, it will be reported in nanomolar. However, you might be studying, wanting to know its rate at a different concentration. I blew that a little bit, but I was trying to highlight to you that oftentimes it can be, some parts of your enzyme kinetics can be reported in a different unit than the concentration that you're interested in determining a velocity for. And it's not just that they're trying to trick you. Well, that was a slight digression, but what was the initial question? Let's just break it down again. What are your knowns and what are your unknowns? Your known, we have the Km, is 24 nanomolar. Okay. We have, in this case, an initial velocity. So it says, when it says it has a turnover velocity of 14.72 seconds to the minus 1, that's what this is. And we're also given a substrate concentration. Of 25 micromolar. Okay, so step one, here is an example where we have two variables that are, their molar concentrations are in different units, and that can't be. You'll be off by a factor of 1,000-fold, either up or down. So I would go to, it really doesn't matter. How about let's convert to micromolar. So 24 nanomolar be surprised, a lot of people still have problems with unit conversion even after they graduate from undergrad. So this is how I do it. You want to get rid of nanomolar, so you're going to do a multiplication factor where nanomolar is going to be on the bottom so that they'll cancel out. And the question is, how many micromolars are there in a nanomolar? Well, nanomolar is smaller, so it's actually for every 1 micromolar, there's 1,000 nanomolars. So in effect, you end up dividing by 1,000. You can move the decimal place 3 to the left, and you'll get 0.024 micromolar. This is the same, but you can see it's very small. Okay? Alright, so in this case we can just go back to plain old Michaelis-Menten equation, which equals Vmax times the concentration of substrate over Km plus concentration of substrate. These were your knowns. Our unknown, in this case we're actually solving for Vmax. So get Vmax on its own, multiply both sides by Km plus concentration of substrate, and then divide by concentration of substrate, equals Vmax. Let's plug these numbers in. Initial velocity is 14.72 seconds to the minus 1 km. Remember, we converted this unit, so let's put in the right one. 0.024 micromolar plus the concentration of substrate. Really in vast excess here. Right. Divided by that really big substrate concentration. Alright, continuing on, if you do the math for this, you should get, I got 14.734 seconds to the minus 1. In some of these I may have rounded, and so you may not have exactly the same answers as me. But here's your Vmax, okay? You could say done, or you could once again take a step back and say, does this answer make sense? So what did they give you in the beginning? They told you that for this enzyme that has a super tiny Km, really high binding affinity, so it's already reached half of its Vmax at 0.0024 micromolar. Right? It was asking you to solve for which part of this graph? Pause and think. Okay? Hopefully your answer is this. This is what you just solved for, the Vmax. Does this make sense? What concentration did they give you? They told you at 25 micromolar, so way out here, 1,000-fold excess. This is not drawn to scale. At 25 micromolar, what were you at? 14.72. So here the VO was 14.72 micromolar, and the Vmax that you calculated was essentially 14.73. What does this mean? This makes sense, is what it means. It makes sense because at 25 micromolar you were basically in that part of your curve where you're asymptotically approaching a limit. Your limit is 14.73 seconds to the minus 1. It's interesting that even at 1,000-fold excess of your substrate, you're not quite there. But for all intents and purposes, you are there. I hope this was helpful. The purpose of making this pencast for you was to help some of you who might have been struggling with the algebra aspect of this, whether it was a one-step or a two-step, or whether you used the Michaelis-Menten or Lineweaver-Burke to get a variable on an individual side. That was purpose one, was math. But the second purpose that I think is actually just as important is to double check that your answers make sense based on what you've learned in this class thus far. See what number you've calculated, and then go back to the parameters that were given to you in the known, and just a quick gut check in each case. Does it make sense?